Okay, in this video I'm going to carry out a path analysis using latent variables. We're using the AMOS program, and the data is coming from the 2018 college football season. So I have an SPSS data file that you can download from the video description at the YouTube site. Within the data set, we have 131 teams with various performance indicators, both offensive, defensive, and overall team performance. So the model that I wanted to test is essentially this one right here. We have essentially a latent variable for offensive proficiency, a latent variable for defensive proficiency, and then sort of an overall team performance latent variable. You'll notice that within this model we have average team passer rating, quarterback sack per game, third down conversion percentage, rushing yards per game. These are all indicators of the offensive proficiency factor. Sacks per game by defense, opponent third down conversion rate, takeaways per game, and opponent yards per game. These are serving as indicators of defensive proficiency. You'll also notice that we have win percentage and red zone scoring percentage serving as indicators of overall team performance. I'll go ahead and say this, that really the red zone scoring percentage really probably ought to be treated as an indicator of offensive proficiency rather than overall team performance. But when I was drawing this out, I was basically trying to incorporate multiple indicators of sort of an overall team performance. But basically by doing that, that's going to create some problems, and I'll show you that shortly. So typically when you are running a path analysis using latent variables, the first step in that process is actually a CFA model where you test the factor structure. So you're basically carrying out testing what's called a measurement model, which is designed to evaluate the degree to which the indicators are good indicators of their respective latent constructs. So that's sort of the first step, and then assuming that the measurement model holds, then you would proceed to specifying the structural relationships among the latent variables. Note too, as you're looking at this model, that we have essentially offensive proficiency and defensive proficiency. These are exogenous latent variables, and they're exogenous because we don't have any predictors of the variation in those latent variables. Overall team performance is an endogenous variable within the model because there are errors pointing to it, where basically we are trying to account for its variation by way of offensive proficiency and defensive proficiency. We also have a covariance that's drawn between our exogenous variables. You'll also notice too that we have I've already drawn in a couple of error covariances for the indicators of average team passer rating and rushing yards per game, and then opponent third down scoring percentage, or third down conversion percentage, and opponent yards per game. So before we actually run this particular analysis, what I thought I would do is I will start off by testing the measurement model. So I'm going to carry out this analysis, basically carry out a CFA model, testing a three-factor model with offensive proficiency, low defensive proficiency, and overall performance. And I'll get to talking about why I'm calling this low defensive proficiency in a bit. So the first thing I'm going to do is actually I'm going to get rid of this error term right here, get rid of these two paths right here, and then just specify covariance between these factors here and these factors here. So all three factors are being allowed to covary. So what I'm going to save this as, I'm just going to call this CFA2 right here and save. And first off, make sure that your data set's in there. It is. And under analysis properties, I'm going to make sure that right now I think I've got some missing data on some of the variables. So make sure that you have estimate means and intercepts clicked when there's missing data. So that is clicked. Under output, I'm going to leave as standardized estimates and squared multiple correlations. So when I press the calculate estimates button, you can see that I get a little chi-square value down here. And if I click on this box right here, you can see that we get these are the unstandardized estimates, these are the standardized estimates. Now, if so far everything looks pretty good. If I go under the if I request the output, you'll notice that under model fit, I can kind of see how well the measurement model seems to generally hold. You can see we have our chi-square goodness of fit test. That's significant, which is kind of an indicator. Well, it's conventionally an indicator of poor fit if it is significant, which it is. We also have the CFI right here. You can see that it's 0.936. Close fit would be more indicated by values of 0.95 or above. Acceptable is about 0.90. The same goes for TLI, and you can see that this is actually less than what's conventionally acceptable at 0.90. The RMSEA value, close fit, is indicated by an RMSEA value 0.05 or below. Acceptable fit is indicated with values up to about 0.08. So you can see that this is indicating poor fit as well. I do want to point out that if you click, you'll see under estimates right here, these are the essentially the unstandardized factor loadings as well as tests. But you'll notice that what's appearing under here, it says notes for a group model. And so above it, you'll have notes for model, and there's nothing that seems to be inherently wrong there, but you'll see that under the estimates, you'll see notes for group model, and you'll notice that it says the following covariance matrix is non-positive definite. And so it says the solution is not admissible. So at this point, there's not really any need to go under model fit and really evaluate those, or to really spend much time looking at the estimates, because there's a problem where the solution would not be considered admissible. And the problem basically is after doing a little bit of investigating before putting this video together, the problem is really this variable right here serving as an indicator of overall performance. And so, if you look at the zero order relations between red zone scoring and win percentage, it's actually on the low side. And it also is more likely that this is probably a better indicator of offensive proficiency than overall team performance. So before moving into testing our model, or actually what I'll do is just kind of show you what will happen. We'll go ahead and specify the original model that I was showing you and show you why that can be a problem. So I'm going to get rid of this and this, and let's just say for argument's sake that I had not carried out the CFA and I didn't see that there was a problem. And I want to go back and I want to test this model out. So let's see what happens. I'm going to also add an error term here, which I will just call this under object properties. I'm just going to name this E11 right there. So in this model right here, this is the same model as what I started off with, which is this one right here. So what I'll do is I'm going to run the analysis. If I click on estimates, you'll notice that again we can still get our various estimates. You can see some weirdness going on with these path coefficients there. Actually, it's just there's nothing too weird about them. It's just, I guess, they're rounded off. But under standardized estimates, you can see that the relationships between offensive proficiency and overall performance is, as you would expect, is positive, and low defensive proficiency and overall performance is negative. But where we have a problem is if we go back under and look at the output, you can see again we have our notes for a model and it says the solution is not admissible. And the reason why is that the error variance for E11 is essentially negative. So you'll see the coefficient, it appears in the output right here as 0 or 0.000, but that's just kind of rounded off. The estimate is actually negative, and if we go under estimates, we can go look further at the error variance for E11 right here. Again, it's sort of rounded off right here, so it might give the appearance of 0, but you see the critical ratio is just a ratio of your estimate to the standard error, and given that this is negative, that's also further evidence that we have a negative error variance. So we have a problem here with that, and again, after I did some investigating, the real problem in this model is this red zone scoring percentage as an indicator of overall percentage. So what we can do instead is there are two options. One option is to essentially eliminate this variable right here and use win percentage as a lone indicator of overall performance. Another possibility, which is also which seems pretty logical, is to still retain win percentage as the lone indicator of overall performance, but then use red zone percentage as maybe another indicator of offensive proficiency. So those are two options that we might use. So I think what I'm going to do is I'm actually going to start off with, I'm going to use red zone scoring percentage as an indicator of offensive proficiency. So what I'm going to do is go back to my original model, and first off I'm going to delete, actually I'm not going to, I don't need to delete that. I'm going to delete this path right here, and I'm going to use my little moving truck guy and move this over here, move this over here, just kind of keeping it all together with my indicators of offensive proficiency right here. And then I will draw a path from offensive proficiency to red zone scoring percentage. So that looks pretty good right there. Now, at this point, because I have a lone indicator of overall team performance, first off, I need to set this path to 1. So I'm going to right click, go to Object Properties. I'm going to fix this, coefficient to 1. Actually, I'm under the wrong thing. I need to go under the arrow and fix the regression weight to 1. And so now it's appearing. And then the second thing I need to do is set the error variance for win percentage to 0. So I'm actually going to click on the E10 error term, and where it says variance, I'm going to fix this to 0 as well. So now when I click out of this, when I run this particular model, once I've saved it and run the model, it should work out fine. Before I do this, though, I thought what I would do is go back and test a 3-factor model with offensive proficiency, defensive proficiency, and overall performance, just to see how well that's working. So I'm actually going to get rid of this structural portion right here, and I am going to create, I'm just going to correlate. Oh, by the way, you have to get rid of this error term right here. So I'm going to correlate these 3 factors. And so I'm going to save this as, and I'm just going to call this CFA 2A. And now when I run the model, you'll notice that it's converged. There are the correlations among offensive proficiency, overall performance, and defensive proficiency. So you can see there's a pretty strong relationship between offensive proficiency and overall performance, positive relationship. Low defensive proficiency, there's a strong negative relationship there, and then also between offensive and defensive proficiencies here. If we go under our view text and look at the output, you'll notice that now there's no notes for a model that's appearing underneath the estimate. So in other words, the model appears to have worked out. When we look at the model fit summary, you can see we still have statistically significant goodness of fit test results. But you can also see that the CFI is, it's closer to 0.95. It's still acceptable. TLI is roughly 0.90, a whisper below. RMSEA is still on the high side, and the P-close test is statistically significant. So we're still not that much better off than what we were before, but it is a slight improvement. Just for the purposes of demonstrating the path analysis with the structural relations specified, I'm going to go ahead and run that analysis. So I'm going to get rid of this arrow and this arrow right here, and I'm going to add in the paths from offensive proficiency and defensive proficiency to overall performance. Now, at this point, offensive proficiency and defensive proficiency are exogenous variables. Overall performance is an endogenous latent variable, so I need to add an error term for that. So I'm going to add in an error term just by clicking on the add unique variable and then clicking over here, and so now it's appeared. So I'm going to click off that button and right click, go to Object Properties, and under Text, variable name, I'm going to give it a name. I'm just going to call this E11. And there you go. So this is now the revised structural model. So I'm also going to save this as well. I'll just call this SEM1 revised. I'll just call it 3 right there. Click on Save, and so now we're ready to go. So now when I click on Calculate Estimates, and by the way, just kind of FYI, the overall fit is not going to differ because we haven't really changed the number of parameters that are being estimated in the model. This model although I'm calling it a path analysis with latent variables, it's essentially a multiple regression model with two predictors of overall performance. It's just that the multiple regression model is being carried out with latent variables instead of the measured variables. So that's why the overall fit of the model is actually not going to be any different. You can see that the values are exactly the same for CFI, goodness of fit test, TLI, RMSEA. Everything's exactly the same. But we can look at the unstandardized regression coefficients and the standardized weights as well. So the actual name of the offensive performance variable is offense P. So what's appearing in the actual figure right here is, if I right click on that, you can see this is the name and the label is what is actually appearing there. So we have offense P is actually showing up in the output. Right here, this would be DF, DFP, and so forth. So that's all it is. So at any rate, going back then, we can see that offensive performance, there's a positive predictive relationship with overall performance is statistically significant. Defensive performance there's a negative predictive relationship that's significant. The thing about this negative relationship, though, is that we have to kind of keep in mind that the defensive performance variable, this is actually reflecting low performance. And the reason why is that if we go back into our figure right here, let's just take a quick look at the factor loading. So you'll notice that first off, kind of just going through the offensive proficiency loadings right here, you can see that red zone scoring percentage is positively related. Average team performance, passer rating performance is positively related. Third down conversion percentage, positively related. Rushing yards per game, positively related. Quarterback sacked per game is negatively related, which you would expect that a team with lower levels, higher levels of offensive proficiency would have fewer quarterback sacks per game. When we look at defensive proficiency, we see that opponent third down conversion percentage is positively related. Opponent yards per game is positively related. So, basically more proficient teams ought to be lower in terms of the opponent third down conversion percentage and opponent yards per game. So the fact that these loadings are positive is actually signaling that we have the latent factor is low defensive proficiency. When we look at sacks per game, you can see there's a negative coefficient right there, and takeaways per game, there's a negative coefficient. So that's why this relationship right here is negative. So basically, we can say that teams that have that are performing better overall, as indicated by win percentage, they have higher levels of offensive proficiency, and in terms of defensive proficiency, we could say that they're actually more proficient, or we could say that they would be lower in terms of low defensive proficiency. So you kind of think about it from that standpoint. So at any rate, that covers this particular demonstration. Really the whole point of this was to kind of demonstrate how to model predictive relationships using latent variables in AMOS and using using the football data. But obviously we ran into a problem specifically with this red zone scoring percentage. It was really a poor specification to begin with. I shouldn't have included that as an indicator of overall team performance, and that's why we ran into those problems with the negative variances and non-positive definite matrices. And so by cleaning this up, by moving this where it needed to be in terms of being an indicator of offensive proficiency and just using win percentage as an indicator of overall performance, we cleaned it up pretty nicely, and now the results are interpretable.